All right, so we're going to go through the Unit 6 review guide. That is our stoichiometry unit. And a lot of calculations, but it's usually not the math that can pose some potential um, problems at some points. It's usually just the correct setups and making sure that you know what you're starting with compared to what you want to end with, unit and substance alike. Remember, stoichiometry is just the ability for us to connect substance A, whatever that may be, to substance B, also whatever that may be. And effectively, it's just a starting amount compared to an ending amount. So A and B are arbitrary in this case. We use the letters A and B just to signify what we have to begin with compared to what we would like to end with. In a given problem. So we do have a mole bridge that we can use that allows us to at least visualize what these steps to take would be, and then that helps us out a little bit. So in terms of going through this, usually I just want to make sure that I start by identifying what I am starting with, and that's whatever I have an initial quantity of. And in this case, it's the 102.3 grams of CO2. And so what I do is I like to make sure that I label the substance A there, so that I know at least what I'm starting with to begin the problem. And then in number, or in letter A, I should say, for number one, the first thing that I want to do is I want to find moles of substance B. I know this is B because it's a different substance, and so in this first problem, CO2 is A and iron oxide is B. All right, and that's just this first example problem. So if it helps, I actually want to just set up the problem with what we're going to start with, and then before I add numbers in, I'm just going to show the units cancel out, and that's going to help me not only identify how many steps I need to take, but also then just plug and play whatever values that I need in order to help me cancel units out and proceed. So for this first one, I know that I'm going to start with what I am given at the beginning, and it makes it a little bit easier and little less daunting, although not necessarily textbook, so to speak, where we would normally just continuously write over and over again the substance formulas. But of course, as those formulas can get a little bit larger and space is limited. What we did say is that as long as we identify what A and B are in a particular problem, there's no reason that you shouldn't be able to substitute the letter A for your starting amount of whatever it is. You just have to make sure you're keeping track of that. And now what I'm going to do is I'm going to add my conversion factors. And in this case, I'm only adding two conversion factors because, per our mole bridge, we want to go from grams of A to moles of B. And so in order to get rid of grams of A, I know that whatever the molar mass is of substance A, it's equal to 1 mole. And then we have a mole to mole ratio. And because this is where I want to stop, that's where I end. And so based on how many conversion factors we use, that's how many additional quote-unquote fractions for our conversion factors we add on. Because then, of course, we're able to cross out any diagonal units comparison to one another. So in order to get this, remember, we need the molar mass of our substance A. In this case, that was carbon dioxide. And so to get the molar mass, you just look at the periodic table, and I know that we have 44.01 grams per mole there. So I'm going to put 44.01. That's just adding one carbon mass as well as two oxygen masses together. And this step right here is where we officially go from substance A to substance B. And at this step, that's where we're using the coefficients in our balance equation. And that's the only time that those values come into play, but those are the mole-to-mole ratios. And so, again, we can kind of show that and lay it out a little bit here, where we say these are the mole ratios between our substances, regardless of which is A and B. Again, we can start with this and here. We can start with that and end here. It's just dependent upon what we want to evaluate up to, and then compared to where we're starting our problem with the given information. So in this case, remember, any blank does represent the coefficient 1. It is understood. And A is carbon dioxide, so I know that there are 3 moles of carbon dioxide for every, I look, and it's 1 mole of iron 2, or iron 3 oxide. And so in that case, that is where I would end, and I solve. And how we solve these problems, of course, is going to the calculator, and we could simplify the top and bottom, divide the numerator and denominator in the end, but instead, it's nicer, I think, when you get used to just taking everything as is and just doing the mathematical operation along the way. Any number that's not 1 on top, I'm gonna multiply. Any number that's not 1 on the bottom, I'm going to divide by. And remember, this 1 here is just a nice little placeholder that helps you get started, show you that the initial amount that we're starting with is truly in the numerator, in order to kind of see that idea of these units canceling along. And so I'm going to click enter, and of course, just hundredths place is usually where we like to go. Mole B, you could put mole B here, or you could represent what B is in this particular problem. That is iron 3 oxide there. So there's that. Down here, we see that these all stem from the same starting point, which is our 102.3 grams of carbon dioxide. So really, these steps at the beginning are going to be exactly the same, being able to go from the mass of carbon dioxide to mole value of carbon dioxide. And then in this case, because I want the mass of this new substance, which now iron is B, I know that I'm going to have 3 bridges. Here's 1, here's 2, here's 3, and our bridges represent our conversion factors. And so this is our step where we transfer moles of A to moles of B using those mole-to-mole ratios above. And we identify that the moles, and I don't know why that happens sometimes when I go to the highlighter, but we know that there are 3 moles of carbon dioxide for every 2 moles of iron per those coefficients in the balanced equation. And then I also know that 1 mole of iron is going to be equal to whatever its molar mass is. And in this case, that would be 55.85 because it's just iron by itself. And now to solve. So I start off with what I am given. I'm going to divide through, not twice, but I'm going to divide through by my values here, times 2 divided by 3 times 55.85, and we end up with about 86.55 grams of B, or in this case, iron. All right, there's that, and then the last step here would be our 102.3 grams of A, because we are starting with, again, that amount of carbon dioxide. And we are going to go to volume of carbon monoxide here. And in that case, that would be liters of CO. All right. And then we're going to make sure that we note that that is substance B here. So I can give you the name, and then you should know that that is the formula. CO is not the same as CO2, as we can see. They are 2 separate things. So we are going to connect the product of carbon dioxide to the reactant of carbon monoxide. And I know that this is going to be another 3-step problem. My 44.01 grams of carbon dioxide equal to 1 mole of carbon dioxide. And my 3 moles, at this point I know that there are 3 moles of carbon dioxide to 3 moles of carbon monoxide right here. And then I have 1 mole of my carbon monoxide. And then instead of going and finding the molar mass of carbon monoxide, I'm not asked for mass, I'm asked for volume, which is our our liters. And at STP, standard temperature and pressure, we know that there are 22.4 liters of any substance equal to 1 mole, and that's going to be our value there. So we know that all of our units cancel out because they are in the appropriate place. 102.3 divided by 44.01. You can do times 3 minus 3. That's going to cancel out anyway, so we don't have to really worry about that. And then multiply by 22.4, and we get 52.07 liters of either B or what B is here, which is carbon monoxide. All right, so there is that. Now, down here, we're going to do some similar things. And I would say that the trickiest part about down here is the idea that I give you just the names, and so for some of these, and just to note that nitrogen and hydrogen gas, when I refer to those as such, it is referencing to diatomic. So whenever if we have to find a mass, we have to multiply their molar mass by 2. So just, again, just watching out for that. So stoichiometry, the process is really just about identifying what you are starting with, not just value to know what number you begin the problems with, but also what unit and substance in our balanced chemical equation that we're working with. So in this case, nitrogen gas is N2. This is going to be A because that's what I have a starting amount for. And I am looking for grams of NH3, which in this case is our B, our ending point. All right, and so because I see the word grams, I'm going to just immediately find the molar mass of this, which is 17.04 grams per mole, just because I know that I will need that in order to be able to use it as a conversion factor, considering grams is something that I'm going to try to obtain. And I, of course, have to go through the unit of the mole to do that. And so we're going to start with our 12 moles of A, which is our nitrogen gas. And to get to grams, I'm already in moles, so I only have to cross 2 bridges. And so there are 2 bridges. The first bridge is going to be our mole A to mole B bridge. And this is going to allow us to bridge the gap between our substances. Remember, there's no coefficient there, so it does just represent 1. And then I have 2 moles of that 1 mole of that nitrogen gas compared to 2 moles of that ammonium. And that ammonia is going to be our new substance, and I know that 1 mole of ammonia is going to be equal to that 17.04 grams. And so that's why I kind of front-loaded that work so I didn't have to just calculate at the end. I could already have that value already there to use. So I'm going to take 12 moles. I'm going to multiply by 2. I'm going to multiply by 17.04, which is that molar mass, and I end up with about 408.96 grams of NH3 there. All right. And again, stoichiometry is just the ability to say, well, if we start our reaction here with 12 moles of nitrogen gas, well, then if all of that is assumed to react completely, then we should be able to produce this much ammonia. And that's going to be something that's useful, especially in lab when you're talking about multiple reaction amounts. So we'll get to limiting reactants here in a second. But let's just do a couple more of these just to make sure we got these all set to go. Remember, nitrogen gas is N2. This is A again because we have a starting amount for that. In this case, I want liters of hydrogen gas, which is H2. And this is going to be B. And so I'm going from grams to liters. This is a 3-step problem. So 528 grams of nitrogen gas, which is A. And in this case, N2, I know that I have grams, so I need the molar mass. That is 14.01, which is the mass of nitrogen, times 2, which gives us 28.02 grams per mole. So again, just front-loading that so that now I can plug it in when I need to. So 3 steps to go from grams to liters, and we have our 28.02 grams of A here. We have 1 mole. Remember, molar mass and volume are all equal to 1 mole at all times. The only point in which you may have a different value with the unit of the mole is when we are going from A to B, because we do use those coefficients from the balance equation. In this case, I start with nitrogen, which has 1 mole equal to 3 moles of hydrogen gas, as we can see from the balance equation. Then I go from mole, 1 mole is equal to 22.4 liters. And so I go through 528 divided by 28.02 times 3, and I'm going to multiply by the 22.4, and I get about 1,266 we'll say 3. We'll round that up. And that is, of course, liters of hydrogen, H2, or liters B. Now, in this case, I want grams of hydrogen, and I start with grams of ammonia in this case. And we actually calculated the molar mass of this before, but I know I'm going to need that because I'm in the unit grams. And then I know that I'll end up needing the molar mass of hydrogen gas, which is substance B, and that's because it's asking me for grams. So I do need to find its molar mass. So now that I have those values, I just start my problem. And see what you see. You can see what I mean by A and B are arbitrary, right? Anything can be, and any substance in a chemical equation can be A. Any substance in a chemical equation can be B. It doesn't matter. What matters is what are you starting with? That's always going to be A. What are you ending with or trying to obtain in the end a value for? And that's going to be substance B. So they are interchangeable. This is a gram to gram problem, so it is going to be a 3-stepper. I know grams of A are equal to 1 mole of A, and grams of A in this case, which is our ammonia, is 17.04 grams. Moles of A to moles of B, that is going to be our 2, right? 2 moles of ammonia in the balanced equation is equal to 3 moles of hydrogen. 1 mole of that hydrogen is then equal to 2.02 grams of hydrogen there. And we go through 335. Sometimes we go a little too quick, and some of these might find some errors here and there, but I try to minimize those the best I can. So here's about 59.57. This is grams, of course, of B, or in this case, hydrogen gas. So that's kind of the initial Stoich that we have done, just being able to identify A and B, and then being able to stop where we need to, not doing more than we need to, like for these 2-step problems or just a mole-to-mole ratio problem, something like that. And then we get to number 3 here, and in this case, this is where we started talking about limiting reactants. And we know that limiting reactants, we are instead not just going to start with knowing one of these amounts, but we're going to assume that we're going to be doing these labs, hypothetically, right, these experiments in the lab. And so what we need to do is take our starting amounts and evaluate how much product each of those could make. Now, we did the s'mores activity that kind of outlined this, and we talked about the hot dog and bun analogy in terms of what runs out first, and that's kind of no different than what happens here. So in this case, what I'm going to do is, because I know that these are all gram A to gram B problems, I'm going to set these up where I have my starting amount, and then these are all going to be 3-step problems, all right? And we do it this way just because grams are a little bit more practical, especially when we talk about going into the lab. And so we do just go to grams. You could do this by stopping at the mole unit as well, but we go through the longer process because we also talk about excess reactant left over and all that fun stuff. So what I noticed helped when we were in class, at least, I figured it was a little bit nicer with the ability that Notability has, is to just identify your starting substances in a certain color. So in this case, potassium is going to be substance A. So we're going to start with 103.5 grams of potassium here. And instead, to be consistent, I will just mark that A. And then we are going to identify what our other starting amount is, which is 94.3 grams of zinc fluoride. And we see that we're not always going to start with the exact same amount of each product. It doesn't really matter. But what we are going to compare is what would the amount of zinc be? So grams of zinc here. Zinc is substance B. And zinc is substance B in both scenarios. And because we need a comparison, we need to be able to develop a way to identify, hey, one of these amounts, either this or this, is going to get used up first. All right. And it's not all going to be in necessarily a perfect ratio between the two. And there's different factors in there, like molar masses of these substances, as well as those mole-to-mole ratios from the balance equation. So what we need to do is we need to evaluate, well, given these amounts, let's just hypothetically say we're putting these things together in the same reaction. What's going to get used up first, right? And that's going to be our limiting reactant. It's also going to produce our what we call theoretical yield. We're going to be limited to the amount of product that we can make. And so I'm just going to identify these up in the equation too. So there's that's potassium. There's zinc fluoride there. And then there's also zinc here. We can see that potassium fluoride is kind of like the odd one out. We're not too worried about that in this problem at all. So we're kind of just going to ignore it. We're going to focus on just the two reactants and then the product that we have been told we want to create. And so we're going to go through this. I'm just going to place a 1 underneath just for consistency's sake. Again, that 1 doesn't really mean anything. But now we're going to really start. So here's grams of A. And then here's, of course, going to be equal to 1 mole of A. And then I know mole of A is going to be converted to mole of B. And I've labeled which A and B are. We have potassium, we have zinc. And then, of course, I know that 1 mole of B is going to be whatever the mass of B is. So in this case, those molar masses are going to come from whatever the substances are. In this case, K, that's 39.10 grams per mole. And B, which is zinc, is 63.55 grams per mole. You know what? Let me double check that, because I like to think I have a pretty good grasp on that. But, I could always make mistakes. So I'll double check, make sure I have this pulled up, but it is 65.39. So hey, good thing I did that. 65.39. I was doing copper. 65.39. There we go. So there's the molar mass of zinc. Now I can go through my problem. In this case, I'm converting the mass of potassium to moles. I am then going to use the coefficients in the balanced equation to connect the two. I know for every 2 moles of potassium, because of that coefficient up there, I have 1 mole of zinc. There's nothing in front. That is an understood 1. And then 1 mole of zinc, not because it's 1 here, just because 1 mole is equal to any molar mass. 1 mole is equal to the 65.39 grams of B there. So there is that, and then we can solve, and we can figure that amount of product out, or that yield. So 103.5 divided by 39.1, divided by 2, and then times 65.39. And that gives us 86.50. We'll do 5, round that up, and that is grams of course, zinc, right? So there's one value. But now we have to do this again, because we also have to identify how much zinc would we now produce if all of this zinc fluoride reacts. And we have to compare, because we're only going to be able to make one of these amounts. So we know that we'll have to find the molar mass of zinc fluoride. That's going to be, of course, our 65.39 plus 19 times 2 because there's 2 fluoride ions, and we get 103.39 grams per mole. Zinc, of course, maintains its molar mass when it's by itself, which is the 65.39. And then we're off. So moles of A to moles of B, and then we have our 1 mole of B is equal to the grams of B, which is, of course, we know by now our mass of zinc there. And we know that there's 1 mole based on our balance equation. So you can see how this portion right here, and I'll erase that here in a sec. This portion from there to the last step, that's going to be the exact same in each of these problems because we are evaluating the same amount or to the same product, right? And so now we just fill in what we have missing here. There is 103.39 grams of substance A, and of course, based on our balanced equation, there is just 1 mole of zinc fluoride there. So we'll go through and we'll calculate this one as well. 94.3 divided by 103.39 times 65.39. And we end up with 59.64. And that is grams of zinc there as well, or grams of B, right? And so now we have 2 different answers here. And so what these numbers are telling us is if all 103.5 grams of potassium react, well, we should be able to produce this much zinc, right? But we also have to take into account that we only have 94.3 grams of zinc fluoride able to react, which we see is only going to produce this much. So our zinc fluoride, this ZnF2, is going to run out before we're even able to make this, right? As soon as we make the 59.64 grams of zinc, our reaction stops because this is no longer present, right? It's all used up in the reaction. And so what this tells us is that this is our theoretical yield, right? This is how much zinc product, in theory, we should be able to make if we mix these amounts of our reactants together. And so what that tells us is I don't have to worry about that 86.55. We're not going to be able to even get to that point. And so this kind of answers E here, part E, which is what will the theoretical yield be? Well, it's going to be the smaller amount of those 2 values that you just calculated. So it would be 59.64 grams of zinc. We are limited to making that amount because that reactant is going to go away first. It's going to get used all up first. And so we identify the limiting reactant. When I say reactant, I am talking about this side of the chemical equation, all right? When we talk reactants, we're talking about the left side of the arrow and those 2 substances, the actual chemical formulas. And so when I go down here, I know that my limiting reactant was our zinc fluoride, right? That reactant right there produced that smaller amount. That's our theoretical yield, which means that our excess reactant, or the one that we have more than we need of, is our potassium, right? Because those are the 2 reactants that I have to choose from. All right, and so now what we can do is we can go a step further. And it does seem a little daunting at this point because you are doing a lot of work for one problem, but if we know that we have some of a reactant left over, then why not figure out exactly how much is left over? And so this is going to be yet another gram to gram problem, and the only difference is what we're doing is we're going to evaluate now based off of this theoretical yield being what we start with, because stoichiometry allows us to, in theory, work with perfect ratios between all of our substances in a given chemical equation. And so what we can do is we can say, if we know, based on these amounts of reactants, how much zinc we should be able to produce, then we can also figure out, based off of that amount, how much of the excess reactant that we had too much of, right? This 103.5 grams of potassium, how much of this actually reacted, because this doesn't completely react, right? We have some left over. And so what I'm going to do is I'm going to start this problem out with 59.64 grams of A, because zinc in this case is now substance A, right? And so what I can do here, just to make that a little bit more clear, is I can say zinc is A, and the excess reactant, remember up there, the excess reactant was potassium, which is now going to be substance B. So we're doing another gram to gram problem. The only difference is we're changing our order. Instead of going from reactant to product, now we're going backwards. Knowing the amount of product that we have, we are able to then use that to figure out how much of that excess reactant do we actually use. Because once we get that, we can figure out how much is left over. And so we have our zinc, which is 65.39 grams, equal to 1 mole. We know that in our problem, 1 mole of zinc exists, and that's equal to 2 moles, if I'm not mistaken, of potassium, which is substance B in this case. And then we know that 1 mole of B is equal to 39.10 grams of B. Right, so what we just did was we identified, based off of our theoretical yield, that smaller value that we calculated above, of zinc, of our product, we should be able to now figure out exactly how much of that 103.5 grams of potassium that we started with we actually use, because we obviously didn't need all of it. And so we end up with 71.32 grams of potassium. And so this is how much this is used. And actually, let's go a step further, and let's just say this is excess reactant used, right? Our excess was the potassium. We have way too much potassium. And so once all of that zinc fluoride runs out, those 94.3 grams, the reaction stops, and then there's a bunch of that just potassium floating around. And so we can actually find that right here in part G, right? We can take this amount used, and we just take what we start with. And so your template here to find a leftover is to take what you start with and subtract what you used. And that's going to get you your leftover. And so in this case, we started with 103.5 grams of potassium, but when our reaction ended and all of that 94.3 grams of zinc fluoride was used up, well, at that point, we had only used 71.32 grams of that potassium. And so we can just take those two numbers and we can subtract them from one another. So that would be 71.32, and we get 32.18 grams of potassium, and that is left over. All right, and that is how we can go through and kind of work backwards. And if you see something that's pretty neat, if you like to see patterns in things, if this helps you, identifying what your excess reactant is, if you look up here, the steps that we took here in this middle portion are the exact same steps that we took here. The only difference is down there we went backwards and we just flipped everything. And so you can kind of see that happen here, where all those values you had up there now just get translated here in a different order, because we're starting with the opposite thing, we're ending with the opposite thing. So that's just something that you can take note of if you like patterns, if you notice that pattern, and if that helps you. All right, but really all we're doing is going from our theoretical yield of zinc or product to the amount of excess reactant that we identified that we actually used. And then the last step, of course, is identifying if we actually have 55.7 grams of zinc. Kind of looking at the reaction above, we can figure out the percent yield, or how efficient or how effective our lab was. This will always be given, and this will always be your actual yield. So whatever number you are provided in this part of the problem, that is your actual yield. So that is what goes on top. And then, of course, your theoretical yield is the theoretical yield above the 59.64. So in theory, that's what we should make. But in labs, not everything always goes according to plan. And so sometimes you end up not making all of the product that the calculation says you should make. That's why we call it theoretical. But this experiment would have been really good in terms of a percent yield, because we see that we have about 93.4%. So we obtained in this hypothetical fake lab about 93.4% of what we should have made, which is really good. So that's how you can kind of look at efficiency of a lab. And so I'm going to go through this one just so that you have another example. You see, I just made a small typo there. It was from the one above. But what I'm going to do is I'm just going to do the exact same thing down here, just so you have something else to base off your examples and to help you through this. So I'm going to do it the exact same way I did before. We're going to start off with our setups, or at least our templates, our 3-step problems here. Gram to gram, in order to identify the theoretical yield, the limiting reactant, and the excess reactant. I'm going to identify the starting amount and substance, in this case potassium phosphate. That is K3PO4. This is going to be substance A up here, and I'm going to mark that there. In this case, 24.5 grams of aluminum nitrate. Aluminum nitrate is the other reactant, which is our aluminum and 3 nitrates. That is A down here. And then it tells you that we are evaluating at potassium nitrate in grams. And so potassium nitrate is KNO3. And so this is going to be B. And that's the same for both. And there's KNO3. This is B. All right. And so we're going to, let me color code these again as well, just like I did above. And there we go. All right. So really we can just kind of ignore the aluminum phosphate on the product side. We aren't really concerned with that. Then we set up our problem. So let's do the potassium phosphate first. This is what I meant by using A and B instead of the actual formulas, because they get kind of long in some cases. So here we start off with 74.2 grams of our potassium phosphate. We'll need to find the molar mass of that, and that's going to be equal to 1 mole. We will have the mole-to-mole ratio here going from A to B, B being potassium nitrate on the product side. And then we know that 1 mole of B is going to be whatever the mass of that is. So let's calculate those masses just so that we have them. And I'll put an arrow up here to it. Potassium, again, is 39.1 grams per mole. And so we have 3 of those. So 39.1 times 3. Plus phosphorus, which is 30.97, and then we have a 64, because 16 times 4 is that. And we get 212.27, so 212 wrong color. 212.27 grams per mole. There it is down here, 212.27 grams per that 1 mole. Let's do the same thing for potassium nitrate, and then we will have it for down here, but then I will also write it over here so that you see it. 39.1 plus 14.01 for the nitrogen, and our 16 times 3 for the 3 oxygen. We get about 101.11 grams per mole, and that's 101.11 gram per mole. And so that's going to be the molar mass at the very end there. In both cases, right? In both cases. So let's fill out the rest of this on the bottom here for the 24.5 grams of aluminum nitrate. And let's also find the molar mass of that too before we forget. 26.98 plus 3 times our 14.01, because we'll have 3 nitrogen and we'll have 9 oxygen per the 3 nitrate groups that we need. That's going to be 213.01 grams per mole. So 213.01 grams of A, which is our aluminum nitrate, equals 1 mole of A. We know per our balanced equation, we have 1 mole of A equal to 3 moles of B. And actually, we didn't do that here. 3 moles of B for the potassium nitrate. 1 mole there. And we actually also have 1 mole of our potassium phosphate there. So that is 1 mole of A at the top there. And then we roll through, and we know that there's 1 mole of B, and that's equal to the 101.11 grams of B. And so we're going to go through each of these problems. So we're going to figure out how much potassium nitrate can be produced by that much potassium phosphate in A. We have 74.2 to start with, divided by 12, or 212.27, times 3, times 101.11. We get about 106.03. That is grams of KNO3, right? So that's how much potassium nitrate can be produced from the potassium phosphate that we started with. Now we're going to do the same thing down below, 24.5 grams of the aluminum nitrate divided by its molar mass, multiplied by the mole ratio of 3 to 1, and multiplied by that 101.11, and we end up with 34.89, which significantly less than above, which tells us that this is going to be our theoretical yield. And that's because we cannot make any more than this if these are the starting amounts of our reactants, so we don't have to worry about that. And so our theoretical yield, again, is our 34.89 grams of the potassium nitrate. And then we have our limiting reactant. Which reactant, our blue or red in this case, created that? Well, it was our red one, which is aluminum nitrate. And then what's the excess? Our excess reactant is, of course, the opposite reactant, which is potassium phosphate here. So K3PO4. And then I want to calculate how much of the excess would be used. And so this is another gram to gram. And remember, at this part, we are now using the theoretical amount of product that we have calculated above. And we're working backwards to figure out how much of that excess reactant do we have. So KNO3 is now substance A down here, right? And so I can write that over here. KNO3, let's get G a better 3, is substance A. And then the excess reactant we identified was potassium phosphate, which is K3PO4. So that is B. And we're going grams of A to grams of B. And we know that we are starting with that as our theoretical, right? And so our theoretical is going to start us off. And we're going to use stoichiometry to figure out how many grams of our excess reactant was actually used to produce that small theoretical amount. And know that, again, we are just going backwards from this, from part A. We're kind of just doing these same steps just in reverse order. And so we're going down here. We know that there's 101.11 grams of that potassium nitrate, equal to 1 mole. We are then going from our 1 mole of potassium nitrate, right? Oh, I'm sorry, 3 moles. That's why I double check. 3 moles of our potassium nitrate to 1 mole of our potassium phosphate. And then 1 mole of that is going to be equal to whatever its molar mass was. And above, we calculated it to be 212.27. Right, so again, these steps right here, we just done backwards and flipped along the way to make sure that units cancel out. So let's see how much we actually use. So 34.89 divided by the 101.11 divided by 3 times 212.27. We get about 24.42. So 24.42 grams of potassium phosphate. This is how much was used. So this is the excess reactant. I'll give you a better one than that. Used. And so to find the leftover, we know that it's whatever we start with minus whatever we used. And of course, we know we used 24.42 grams. And what did we start with? Oh, we started with 74.2 grams of that excess reactant. So 74.2. And so we just subtract those. 74.2 minus 24.42. And it gives us 49.78 grams of potassium phosphate that was left over. All right, and last but not least, of course, our theoretical yield, or our percent yield. Remember, our percent yield is equal to the actual. I told you would always be given the actual in this particular part of the problem. So we're going to say, let's pretend we did this in lab. Things happened, errors happened, math did math, and then we ended up with an actual yield of 28.5, even though we were supposed to get 34.89 grams based on our calculation. So something happened, and so that's what goes down here at the bottom. And of course, multiply by 100 to get a decimal. And so we take our 28.5 divided by 34.89, and we end up with 81.7%. So still not bad. Not bad. Anything above 70, especially for our class, is pretty good. But that is Unit 6 in a nutshell. So hopefully this helps, and hopefully the color coding down here helped a little bit too. But just make sure that you concentrate on really keeping everything situated in terms of being able to label problems, being able to identify substance A versus B, knowing that it can change depending upon what you're starting with, what you're trying to find, and then knowing, of course, how to use your mole bridge as well, because you'll have that on your test. So if you end up having some more questions, feel free to reach out and let me know. I hope this helped. See you later.